Hello guys, thank you so much for being with me in another artificial neural network tutorial video. We said that if we have a cost function with the help of which we can find the W's, our problem is solved. Now the question is what this cost function should be. For simplicity, we have considered the three classes. It doesn't matter which classes these three classes are, only the goal was that the number of classes is more than 2. Because the two-class problem is a special case of the multi-class problem, here from the beginning we assume that the problem is multi-class. We do not turn the problem into several two-class problems. Here we have a series of inputs which have also been given to us. We want to express numerically whether these were good or not. For the first data, the image is a cat, and we can see that our model has not been able to maximize the score for the cat class. So the values were not good for the first data. They worked well for the second data, and you can see that they were very bad for the third data. We use the SVM cost function to express whether it is good or bad. SVM stands for Support Vector Machine. With the help of this function, we express the goodness or badness of W in numerical form. Behind the scenes, we have a matrix W. We have nothing to do with it here. We have multiplied these W's in the input vectors, and these numbers have been obtained. These numbers are points. We denote these points with S. S is a vector. There are as many classes as there are. We calculate the error for the data I. We have assumed that we have the W's. The ith data is yi. In the training set, we have both the input and the correct output. So the yth data is this couple of xi and yi. Yi is a number. It is either 0 or 1 or 2 because we have three classes here. Yi represents the ith data class. We calculate the value of the cost function, which is loss here, for data, which is actually we can call it a loss function too for data I. We wanted the W's to be such that the score of the correct class is higher than the rest of the classes. These can be calculated mathematically. SYI is the score of the correct class, and SJ is the score of the rest of the classes. Ideally, the score of the correct class should be higher than the score of the rest of the classes. Here, to make sure we consider confidence margin, you have always seen this discussion in SVM. We want the score of the correct class to be at least 1 more than the score of the rest of the classes. These are just rewriting formulas. If this relationship holds, the classification is done correctly and there is no error. But if the result of the difference of Sj and the Syi plus 1 becomes positive, we have an error equal to the positive value. That is, if the result is negative, we do not have an error, and if it is positive, we have an error equal to the resulting number itself. So we have to get max. We have 2 j's here in this simplified problem. For example, here is the correct class is the car class. We check that This 4.9 is more than 1.3, so there is no error. 4.9 is more than 1 plus this 2, the score of the frog class is 2.0. If we plus it with a 1, it would be 3, and still this 4.1 excuse me, 4.9 is higher than the result of this addition. So there is no mistake here either. 0 plus 0 becomes 0. So we are not wrong about the second data. But in the case of the first data, 3.2, if we consider that as the correct class is cat and its score is 3.2, and here the score corresponding to the automobile class is 5.1. If we add a score to this score, it would be 6.1, and the score of cat class is not higher than the score of automobile, neither the score of automobile itself nor the score of automobile class plus 1. But this score is higher than 1 plus the score of frog class. Since if we calculate the sum of these errors, you can see that finally the error is 2.9. So we consider this 2.9 as an error with similar explanations. The error for the third data is also 12.9. We had 3 data. Using this formula, we calculated the error for each, as the total data error is equal to the average of these LIs, which are the errors. So the connection of this discussion with SVM is the margin of confidence. And now if we apply this total to all data and classes and do not exclude the correct class, 1 unit will be added to each of the errors, so 1 unit will be added to their average. So it will not make any difference, and the minimum point will not change. If we use the average instead of the sum, the minimum value will change and will be equal to the current minimum value divided by the number of classes, but the optimal point will not change. Now if we use the square of this relationship, the minimum point may also change. We do this in some cases. The goal is to find a cost function that minimizes it to reach a good W. It doesn't matter what this function is. The important thing is that it leads us to a good W. The lowest value for this function is 0, and the highest value for this positive function is infinity. Last point, first we choose W's randomly. These numbers are usually very small values close to 0. This is the starting rule of the gradient descent algorithm. Is it possible to determine the starting value of this cost function at this moment? Yes. The scores are the product of W in the input vector, so Sj will be almost 0. So by placing it in the formula, we see that the cost function is almost equal to 1 less than the number of classes. With this, we can check at the very beginning whether our algorithm works well or not. In machine learning algorithms, you can never be sure that the errors are zero. Errors are almost always there, and with these techniques you can get a little peace of mind that these errors will be less. Finding these errors is not always an easy task. Okay, I will transfer the explanations about the optimization to the next video. Have a nice time.